Hello and welcome. Today we're going to be doing some examples. In this video we're going to be doing some examples of Gaussian elimination and also explore more of what it means to be in reduced row echelon form and how to read a matrix in reduced row echelon form and know how to interpret and define its solution. Okay, so let's start with a linear system. We're going to do now a 3 by 3 linear system, and the linear system is x1, or so let's go x plus 5y plus z is equal to 2, and then we'll have a 2x plus y minus 2z is equal to 1, and then finally the third line will be it'll be x plus 7y plus 2z is equal to 3. All right, so the first thing we always do is transform this into matrix form. So we're going to have 1, 2, 1. That's the first column, all the x's. This will be the x column. And then we have a 5, 1, 7. That's the y column. And then finally we have a 1, negative 2, 2. And then if you want, some people put a little dotted line to represent the right-hand side is now 2, 1, 3. Okay, we're going to use Gaussian elimination. Of course, the first phase of Gaussian elimination is really identifying this lower triangle here and using row operations to get those to be 0. Okay, so that's phase 1. So of course, so Gaussian elimination, phase 1 is lower triangle of zeros. Using row operations. Okay, so row operations. Remember what the row operations are again. We can scalar multiply any row by a non-zero number and replace it with that new row. We can also exchange rows, and we can also multiply. We can add scalar multiples of rows together to create new rows. So see the previous video for more details about that. Instead of writing down a definition, let's go and actually just do some examples to show what I mean. So the first thing we see here is I see a 2 and a 1. So I want to get, the first thing of course is always get zeros in the first column below the leading entry. All right, so we see what we first need to do. What I'm going to do is I always leave a little margin over there, and we're going to take my first row, and I'm just going to copy it down because we're not going to do anything to that row. On the second row, what we're going to do is we're going to take negative 2 times row 1, add row 2 to it, and that's going to be my new row 2. All right, and that by definition puts a 0 in that first, in that second row of the first column. Right here, okay, so negative 2 times 5, that makes a negative 10, plus 1, that makes a negative 9, right? Finally here you see that if I put a negative 2 times 1, and we add negative 2, we get a 0 there, and in that row of the third column. And then finally, what we're going to do is now multiply 2 by negative 2, we'll get a negative 4, plus 1 means we're going to result in a negative 3. Again, I'm going to put that dotted line there just to highlight. All right, now I need to make a 0 there, so what I'm really going to do is take negative row 1 plus row 2, or sorry, row 3, and that's going to be a new row 3. All right, so that will, by definition, deliver us a 0 in that row down there. Okay, so now we have to take our 5 and subtract it from 7, and I get a 2. I'm taking a 1 and subtracting it from the 2, and I get a 1. And then finally a 2, and I subtract it from 3, and I get a 1. Okay, so there we go. We've certainly now made a simpler linear system, one that has zeros in below the leading term there, in the top term there. We're getting zeros in our lower triangle. All right, the next stage, what we need to do is now look at this second row, and I see there's a -9 and -3. I see a common factor in there. So what I'm actually going to do is divide by -9. So the next stage, what I'm going to do, I'm going to put that symbol there, which means that whatever operations I'm doing are going to preserve the solution space for this system. So what we see here is I'm going to actually take row 2 and divide it by -9, and that's going to become my new row 2. I'm going to rewrite that, and that's going to be really simple to do. 1, 5, 1, 2, and then we have a 0. Now we have a 1 right there, and then a 0, because that 0 divided by -9 is still 0. And then finally, now we're going to get a positive 1/3 in that final position there on the right-hand side. Okay, so now I'm going to rewrite that final row there. We see now I've got ones. I have ones there, a 1 there, and a 1 there. I still need to get this one zeroed out. So the next thing I'm going to do is do my similarity, my matrix similarity. Means they have the same solution space. That's what that symbol means. And then finally I'm going to take now, I'm going to add a -2 row 2 plus row 3, and that's going to be my new row 3. So I write out my matrix. I'm not going to do anything to row 1, and I'm not going to do anything to row 2. All I'm going to do is change row 3. And by definition, by adding a -2 row 2 to row 3, I get a 0 in that position. At 0 plus the 1, I still get 1. And now I'm going to add -2/3 to a 1, which means I'm going to be left with just 1/3 remaining. Okay, so phase 1 is done. Now what I have this matrix is what it was called in. It's in echelon form. And that means what we have here is what we call these here are the fronts of the echelons, and these are what I call the leading entries. That are on a diagonal. We have zeros below them, and they're all ones. Okay, and that's called an echelon matrix. What we want to do next is now phase 2, which is put a system in reduced echelon form. And what that means is now I want to make zeros out of any entry that's above one of my leading entries. Right, and so in this case I need to zero out the 5 and the 1 there using row operations. So that's what we're going to do now on the next page. Okay. So let's do that. So again, let's write down my matrix. It was 1, 5, 1, 2, 0, 1, 0, 1/3. We had a 1/3 over there, and a 1, and a 0, and a 0. Okay, all right. So now what we're going to do is we're going to do my similarity symbol, which means that I'm preserving the solution space, and I want to add a -5 row 2 to row 1. So -5 times row 2 plus row 1 is going to be my new row 1. And by definition, because you see we have that lower triangle of zeros, that's the Gaussian elimination gave us that. Now when we move up to add up, this 0 won't affect the leading entries. And that's why we do it the way we do it. Okay, we see that's going to give us a 0. And that actually doesn't change anything because -5 times 0 is good. But now we have 5 times, a negative 5 times 1/3. I might want to go over here on the side here. Negative 5/3 plus 2/3, which is actually 6/3. That's going to be equal to 1/3. So now I'm going to put that 1/3 up there. All right, and then we have a 0, a 1, and a 0, and a 0, a 0, and a 1, and then finally 1/3, and then a 1/3. Okay, we have one more entry up here to get rid of, and now I'm going to have to subtract this row from that row to get it. So the next stage of my thing is now I'm going to take row 3, I'm going to subtract it. So I'm going to go minus row 3 plus row 1. That's going to be my new row 1. So we have 1, 0, 0. Now the matrix is getting really easy to write. And by definition, that gets rid of that. And so we had a 1/3, a 1/3. And then finally, so a 1/3 minus a 1/3 is a 0. Okay, so there we go. Now this matrix is in reduced row echelon form. So reduced row echelon form means, again, lower diagonal of zeros, lower triangle, so this is what it means, a lower triangle of zeros, and every leading entry those are the ones on the diagonal here. So every leading entry of ones has zeros. Zeros everywhere else. In the column. So one thing to note is that this, you see, it's a perfect diagonal. In some other matrices, it may not be a perfect diagonal. It might be a little bit more jagged. And we'll see that in the next example. All right, but what's important here is now we can actually clearly see, so elimination reveals the solution. Very simply, we can clearly see that x is equal to 0, y is equal to 1/3, and z is equal to 1/3. I can package all that up and actually say that is equal then to my solution set, which is just a single point. All right, so that's very nice. The next thing we want to do now is I'm going to talk about another example, one that it won't work out to have a single solution. There'll actually be multiple solutions. And we'll see what the reduced row echelon form reveals in that case. All right, so let's talk about that example. So now this is going to be example number 2. So let's write it down. It's going to be x1 plus 3x2 minus 15x3 plus 7x to the x4. All right, and then we'll have an x1 plus 4x2 minus 19x3, and now plus 10x4. And this is going to be equal to 0, and that's going to be equal to 0. And then finally, 2x1 plus 5x2 minus 26x3 plus 11x4, and that's also going to be equal to 0. So this is a special type of linear system. This is what's called a homogeneous linear system. And that's because it's equal to 0 on the right-hand side. And so actually when we write our matrix, this right-hand side we don't even need to write because it's always going to be 0 in that column. We'll learn more about what homogeneous means later on. For right now, we'll just say that's what this is, and we'll leave it at that. But it turns out linear systems that have all of the variables, all the linear expressions equal to 0 with no constant other than 0, have very neat properties, and we'll talk about them later. But for now, let's just write it as our matrix. The first column will be the x1 column, 1, 1, 2. The x2 column will be 3, 4, 5. Negative 15, negative 19, and negative 26 will be the x3 column. The x4 column will be 7, 10, 11. And again, I don't need to write those zeros over there. We've got it from here. All right, so let's get this and let's reduce this using Gaussian elimination to reduced row echelon form. Right? Again, the idea is all of these linear systems that we are producing through row operations, they all have the same solution set. That's the ultimate fundamental principle that we're operating on. We can find the solution because we don't change it. We simply uncover what it is using the row operations. All right, so we see immediately I want to get rid of those down there. So I put my similarity symbol, and then because I'm going to use this first row as my tool to simplify that lower triangle, I just write it up there. And then I have 1. So what I'm going to do, I'm going to have to redo that. I have to give myself space so I can plan out what I'm doing. This is really important. I think it's incredibly important to have good bookkeeping when you go about this. So what I'm going to do is I'm going to take minus row 1, add that to row 2, and that's going to be my new row 2. All right, and that's going to give me a 0 there. All right, again, I'm subtracting, so that's going to yield 1 there. Negative 15 will become a positive 15 plus 19, and I have what's left over is 4. And then I'm at minus 7 plus 10, I have 3. Okay, that's good. Now, what am I going to do here? I'm going to take a minus row 1. Actually, no. I'm going to take a minus 2 row 1 plus row 3, and that's going to be my new row 3, and that will deliver me a 0 in that lower part of that column. So again, I have to take minus 2 times the 3. That gives me a negative 6. I'm going to add that to 5, so I'm going to get a negative 1 there. Right, and then so that becomes a positive 30 plus negative 26. That gives me a 4 there. Oh, this should have been a negative there. I made a mistake. We saw that. Okay, so I'm going to go back here a second. I'm taking a minus row 1. That gives me a positive 15. I'm adding it to negative 19. That gives me a negative 4 there. Okay, thank you very much. Sorry about that. And now we're going to go back to this. So I see I'm going to multiply this by negative 2. I get a negative 20. Then I'm going to add it to a positive 11. I'm going to get what's going to be left over from that. I'm multiplying this by negative 2. I get a positive 14. Negative 14. I'm going to add that to 11, so I'm going to get a negative 3. All right, so sorry about that. I got a little tripped up, but we're all back on good footing here. All right, do we see here there's something really curious? We see these two rows are very similar, are the same, are basically minuses or negatives of each other. Okay, so this is going to be interesting. What we're going to have to do then is, sorry about that, I want to turn off my noise there for a second. All right, so what we're going to do then, the next phase is to add these two rows together. We see that's going to do something very interesting. So now I'm going to, again, I give myself room. I'm going to write row 2 plus row 3. That's going to be my new row 3. So again, we write the top row here. We don't change anything. And we write row 2 to be the same thing as well. And then we see when we add these two rows together, everything cancels perfectly. So this sometimes happens when you're doing row operations. So we get basically a row of all zeros. Okay, so what to do in this case? This is just how the echelon works. We see these are my leading entries. So this is now an echelon matrix. Okay, this is my echelon matrix, and these are my leading entries. Okay, so those are my leading entries, and we see basically what it shows here, there's no leading entry here. Okay, on this third row. And that just happens sometimes. And what it really means then is actually, although it looked like we had 3 equations, one of the equations actually had no additional information that the other 2 didn't already have. And so through the row operation procedures, one became entirely 0. So as to take an aside here, what we can see is let's do a little mini example. If I have this is a 2 by 2 linear system. If I have x plus y is equal to 1, and then I have 2x plus 2y is equal to 2, this is redundant because it's just a scalar multiple of the first row. It has no new information in it, so we don't need it. And in fact, if I did a row operation, I could get rid of this row. And that's exactly what happened here. It turned out this bottom row didn't have any information that wasn't already in the other ones. So it was irrelevant to the problem. So now let's see if we can go further. We need to do now phase 2 of the Gaussian elimination, which is get rid of that 3 that's in the leading entry. Because there's no leading entry in the bottom one, we can't get rid of anything back here. But I can still get rid of that one. So that's what I'll do. I'm going to put that aside there and put that in a box and move on down here. And so now what I'm going to do is I'm going to take minus 3 row 1, or sorry, row 2, and add it to row 1. And that's going to be my new row 1. And what we have here is a 1, 0, and a 0. A 1, and then by definition we get a 0 there. And if I take a negative 4 times by negative 3, I get a positive 12, and that leaves me with a negative 3 there left over. And if I take a 3 and I multiply it by negative 3, I get a negative 9, and I add that to 7, I'm going to get a negative 2 there. All right, negative 4 and a 3. And then finally 0, 0, 0. Okay, so this matrix here, this is as far as we can go. This is now in reduced row echelon form. And here we see our leading entries are right there, a row of zeros. The leading entries, they have zeros everywhere else in their column. And then we have all the back markers back here. We can't do anything about them. But now, the question we have then is, what is the solution space in this case? Well, it turns out it's going to be more interesting. So what we're going to have to do is actually unwrap this linear system and turn it back into something we can kind of see more clearly what the solution is. So let's write that up again. This is going to be 1, 0. Negative 3, negative 2, and then we have a 0 and a 0, a 1 and a 0 and a 0 and a 0, and then we have a negative 4 and a positive 3. And now we have to think about this a bit. So I'm going to put this back into forms with the variables in it. So this is going to be an x1, and it's going to be a minus 3x3 and a minus 2x4. And this row here is going to become an x2 minus minus 4x3 plus 3x4. And this is the linear system now. This has same solutions as original linear system that we saw on the previous page. But let's see now, and remember this was equal to 0 and that was equal to 0. Sorry about that, that needs to be put in there. All right, so what we can see clearly is that I can actually set now x1 and x2 are actually functions of x3 and x4. So I can write this as follows. x1 is actually 3x3 plus 2x4. And x2, now I'm going to the second row here, is actually going to be 4x3 minus 3x4. So what we say here is actually, what we conclude then is x3 and x4 are free parameters. Okay, so there's no constraints on them. There are no constraints. And once you choose an x3 and an x4, then x1 and x2 are given to you. They're delivered to you. And so what we actually like to do is actually define what we call dummy or free parameters variables. And I'm going to say let s and t be real numbers. And they can be any real numbers. Okay, and then what we're going to say, and they are, of course, two free parameters. And again, we could leave it like this. You could just say this and say that these are free parameters, and that would be a very adequate solution to the problem. This actually defines what the solutions are. Okay, but I'm going to go a step further here, and the idea is if we just come up with these artificial parameters, these s and t, it turns out we can just clarify a bit more about what the solution looks like. What we actually say then is that we say that x3 then is going to be equal to s, and x4 is going to be equal to t. All right, and then x1 is actually going to be equal to 3s plus 2t. Right? I've just replaced x3 and x4 with s and t. And then x2 is going to be equal to 4s minus 3t. Okay, and this is a slightly clearer solution. And then what we'll say actually is where s and t are real numbers, and I say that they're elements of the reals, and that's what that symbol epsilon means. It means elements of the reals. So this I could call my solution set. So we can say, well, what does this mean? Why are we using the s and t? And the idea is that it clarifies something important about solutions, that x1, x2, and x3, and x4 are 4 dimensions in the solution space that we have. They're the 4 dimensions of variables that we have. And s and t we can think of as coordinates within that system. All right, so I'm going to end with a little bit of a metaphor to kind of understand why we use the s and t. So I like to use the idea of a marionette. So this is like one of those puppets, kind of like a puppet. So we already know that puppets are, a marionette's always, you have like a stick across sticks like this, right? So we say that this dimension, of course, up down here, that's s. And this dimension here, that's t, right? And we can, of course, and there's strings attached. Of course, we have our puppet, of course, has arms like that, and they're connected. And this, of course, maybe will be x1, and that'll be x2, if you will, and then the puppet, of course, might have legs like this, and that's also attached by strings. And that'll be my x3 and my x4. So again, this is just a metaphor. All right, and the idea is that S and T are the control parameters. And down here, this is what you see. See on stage. All right. That's what you see on this puppet will move up and down. Its limbs will move in all sorts of ways, but there's only two variables that control this thing. And this is what you see on stage, and that is x1, x2, x3, and x4. Those are what we call the observed variables. And that's why we like to highlight how this works, how the S and T are these control parameters that they're actually what the puppeteer would control. X2, X1, X3, X4, those variables are what are observed that are a result or a function of S and T. So I hope that clarifies why we set up our solution space the way we do. Thank you very much.